This is the video for section 7.2 notes, slides 14 through 17. All right, so what we're talking about in this section is something known as the definite integral. All right, so what we've been doing over the past couple of days is by using Riemann sums to estimate the area under a curve. Okay, but at the end of section 7.1, we talked about finding the exact area under a curve. Okay, by using a process that looks actually very similar to this, but it's slightly different. Instead of n approaching zero, instead of n approaching infinity, now we're letting the norm of the partition approach zero. So the key is that in order to find the exact area, right, we said, oh yeah, well, you just have to use an infinite number of rectangles. So if n approaches infinity, what's wrong with that? Well, let's say that I have a graph here, something like this, right? And let's say that I have a partition that is not uniform, meaning that some of the intervals are wider than the others, right? So let's say I have an interval here that is that wide. And then I have really small intervals here, here, right? And so let's say that I have one rectangle that takes up this much, and then the rest here is an infinite number of rectangles. Okay, so now the question is, how many rectangles have I used? Well, technically, this infinity plus 1. Well, infinity plus 1 is still infinity, right? So I have used an infinite number of rectangles. But the question is, do I have the exact area under the curve? Well, for this portion, I do have the exact area, but for this portion, I have quite a bit of an underestimate. And so the fact is that this would not find the exact area under the curve from A to B, even though we've used an infinite number of rectangles. So what we need to do is we need to let the norm of the partition approach 0. So if the norm of the partition approaches 0, then using an infinite number of rectangles is guaranteed to find the exact area under the curve. And so what we want to recognize is that this gives us what we call the definite integral. All right, and so we have the integral symbol, of course, from A to B. So now this is how we distinguish a definite integral from an indefinite integral, what we did in Unit 6, okay, of f of x with respect to x. So this is the definite integral of f of x from A to B. All right, or also known as the algebraic area of f of x from A to B. All right, so algebraic area, what does that mean? Well, what we are used to finding in geometry is what we would know as the geometric area. So geometric area is simply the area that is bounded by a particular shape, all right, or by particular parameters or whatever. Okay, but algebraic area means that wherever the area is depends on whether it's positive or negative, all right? And so, for instance, if I have a function that looks like this, an area that is above the x-axis is a positive area, and the area that is below an x-axis is a negative area. And so that's what algebraic area refers to and how it is different from geometric area. All right, so first thing that we want to do is we want to understand this thing, which is the limit definition of the definite integral. Okay? All right, now there's a slight typo. There should not be an F right there. All right, so anyway, so the limit as the norm of the partition approaches 0 of the sum from k equals 1 to n of w sub k squared plus 2 times w sub k minus 3 times the delta x sub k. So what we need to recognize is that the delta x sub k just stands for the dx, right? The with respect to x, the infinitely thin width of the rectangle. And then this represents the height. Now you'll notice f of w sub k was in our formula, and that translates to f of x. So really, this is just x squared plus 2x minus 3, right? So we're doing what? We're going to integrate that function, x squared plus 2x minus 3, with respect to x, from negative 2 to 5. So negative 2 to 5. That's it. All we're doing is expressing this as a definite integral. And so then we need to have a conversation about what that definite integral actually is finding. Well, we said it's the algebraic area, right? So what does that mean? Well, it's the area under the curve, or it's the area that is bound between the curve and the x-axis. All right? So, Okay, couple properties of definite integrals. Okay, so what did we say? We said that the definite integral from a to b of f of x dx. Well, what does that find? We just said very simply, here's a, here's b. The definite integral finds the area under the curve from a to b. All right, so the area under the curve from a to b is equal to the opposite, the negative of the integral from b to a of f of x. All right, so what does that mean? Well, if I'm going backwards, if I'm going from b to a, then that area is negative, and it's like we're losing that area. All right. The next property, the integral from a to a of f of x is 0. I think that one's pretty easy, right? If it's from a to a, there's no width, right? It's a 0 width, not like a infinitely small. It's actually 0 from a to a, so that is always 0, right? So that's pretty easy. All right, so let's answer some of these questions. If the integral from 2 to 5 of g of x dx is 6, okay, then what's the integral from 5 to 2? Well, remember up here, the integral from 2 to 5 is the opposite of the integral from 5 to 2, right? So really, if this first integral is 6, then this is negative 6, right? Super easy, okay? Next one, integral from 2 to 2. Well, of course, we're just using that property. That's 0. That's easy. All right, but what about this one? Actually, this is a typo as well. It should say g of w dw. What is the integral from 5 to 2 of g of w dw? Well, the variable is really just a placeholder, right? It could be anything, right? The integral from 5 to 2 of g of s ds, or the integral from 5 to 2 of g of a dA, right? Whatever we put in there, they're all equal. So what does that mean? The integral from 5 to 2 of g of x dx, right? Those are all equal. So really, the integral from 5 to 2 is just negative 6, just like it was in problem number 8. Okay? All right, now what about this one? This is kind of interesting. A lot of people struggle with this, right? They say, oh, okay, well, this is easy. The integral from 2 to 5 of g of x, well, look at that. That's just 6. So 6 plus 3 is 9. No, this is not true. Why? Well, because remember, you're told that the integral from 2 to 5 of g of x is 6, but only the integral of g of x. This is g of x plus 3. So how do I deal with that? Well, we know that the integral of two things added together is really the integral of g of x with respect to x plus the integral of 3 with respect to x. Now, we would have done that for an indefinite integral, so it works exactly the same for a definite integral. So the integral from 2 to 5 of g of x dx plus the integral from 2 to 5 of 3 dx. All right? Now, the first one, well, that's what we were given. The integral from 2 to 5 of g of x, that's 6. Plus, how do we deal with this? Now, yes, I understand we know how to integrate 3, but what do we do with the 2 and the 5? All right, so let's think geometrically speaking. What is y equals 3? Y equals 3 is a horizontal line. Here's y equals 3, right? So y equals 3 is a horizontal line, and we want to know the area under the curve from 2 to 5, right? Isn't that what we want to know? So this is really just, it's just a rectangle, right? It's 3 units wide, and it's 3 units tall. So that area is 9. Right? So that means this overall integral is 15. Okay? It's a really easy concept here, but a lot of times people make a mistake. All right? So that's slide 15. All right. So now let's go one step further. Okay? Let's think a little bit here. All right. So I'm given this picture of f of x, and then I have various values in here. So I have 15 representing the area inside of that region, 8 representing the area inside of that region, and 6 representing the area inside of that. Now, these areas are technically geometric areas, right? All I'm telling you is this is how much space is taken up in that region, all right? Now, 15 is above the x-axis, so that's a positive area, and 8 is below the x-axis, so that's a negative area, and 6 is above the x-axis, so that's a positive area, all right? So, if I say, what's the integral from of f of x from a to b? Well, what is that going to be? Well, that's going to be the integral from a to c plus the integral from c to d plus the integral from d to b, right? So very simply, right, the overall integral is 15 plus negative 8 plus 6, right? So really, that means that the overall integral is 13, right? All right, so that's easy enough. All right, now what about 12? It says the integral from a to d of f of x minus the integral from b to d of f of x. All right, so what's a to d? Well, a to d is here, right? So a to d would be 15 minus 8, right? 15 minus 8, right? So that'd be 7. Minus the integral from b to d. B to d. Now we're going backwards, aren't we? So can I rewrite that, right? Instead of going backwards, can I flip this and rewrite it as the integral from d to b of f of x, right? If I do that, then what do I have to do? I have to bring another negative outside. And so 7 minus negative integral from d to b. What is the integral from d to b? It's 6. So 7 plus 6 is 13. Well, what did I do? Think about it. I had the integral from a to d, and I was subtracting the integral from b to d. Well, isn't that really like adding the integral from d to b? So isn't this really just the integral from a to b of f of x dx like we did in the first one? Yes, it is. All right, what about 13? All right, I have the integral from c to b of f of x, so c to b of f of x, minus the integral from a to c of f of x. All right, so what I'm going to do all the time is I'm going to look at these limits. I'm going to say, okay, c to b, that is in order from left to right. C to a is not. So I'm going to flip those. I'm going to rewrite this as the integral from c to b of f of x minus, all right, now if I flip, instead of c to a, if I make it a to c, right, then I have to put a negative out front. And so if I have the integral from c to b plus the integral from a to c, what am I going to get? The integral from c to b plus the integral from a to c. Well, that, once again, is just the integral from a to b of f of x. All right, so now, one thing that I want you to realize, if I have two integrals added together and they have the same limit on the diagonal, then we can combine them and just say from a to b. Okay, same thing was true over here when I flipped that. All right, I had the d's on the diagonal, so it was just the integral from a to b. All right, so let's try that here. And of course, this answer is still 13, right? All right, let's try this one. I have the integral from d to b. So is that in order? Yes, d to b. D to c, is that in order? No. So we're going to flip that. We're going to write that c to d, and we're going to bring a negative out front. So I have the integral from d to b of f of x minus the negative integral from c to d of f of x. And so the d's are the same on the diagonal, and so this result is the integral from c to b of f of x. Now, it's important that you remember this can only be the case if the two integrals are added together. All right, so the integral from c to b. So now look at the picture. What is the integral from c to b? It's negative 8 plus 6, so that would be negative 2. All right, last one here. I have the integral from a to d of f of x plus the integral from d to c. Well, these d's are already on the diagonal, so this is going to be equal to the integral from a to c of f of x. Okay, and so what is the integral from a to c? Well, it's just 15, right? So that is a little bit of graphical understanding of the definite integral. All right, so that's slide 16. All right, so now let's move on to slide 17. All right, so now it says evaluate each integral graphically. All right, so what does that mean? So I have to figure out what a graph is of this thing. So what's the graph of 4x plus 2? Well, it's a line with a slope of 4 and a y-intercept of 2, so something like, not just that, sorry. Okay, so now I want the integral from 0 to 2. So here's 0, here's 2. What am I interested in? The area under the curve from 0 to 2. All right, so this is just a trapezoid. It is 2 units wide, right? So that means 1/2 the height, which is 2, right? The height, quote unquote, of the trapezoid. And then base 1, so I need to know that distance. All right, so what is that? Well, if I plug 0 in, I get 4 times 0 plus 2 is 2. So that height is 2 plus this height, base 2. All right, so now I plug 2 in here. 4 times 2 is 8 plus 2 is 10. So 10. So half of 2 times 2 plus 10. So half of 2 is 1 equals 12. So the value of that integral is 12. All right, next one. All right, same idea. All right, I have the graph of 3x plus 9 looks very similar, right? And I want the area from 0 to 3. All right, so 3 units wide. Base 1 is going to be 9. Base 2, 3 times 3 is 9, plus 9 is 18. So half of the width, 3 times 9 plus 18, right? 9 plus 18, 27 times 3, 54. So half of 54 is 27. That doesn't seem right. Sorry. Not 27 times 3 is not that. It is 63. No. Oh my goodness. 81. I'm sorry. 81 halves. All right. There you go.